Time. What an amazing thing. We're going to talk about why measuring time brought us from being cavemen to where we are today. Without being able to measure time, we would not have evolved in our understanding of the world or even the universe. We wouldn't know what direction we were going in. We wouldn't be able to find far off lands. We wouldn't be able to load Google Maps on our phones. We wouldn't be able to find our local Starbucks. And in fact, your phone wouldn't even exist. But Earth time is constantly changing. Okay, time fans. So those of you who enjoy mechanical marvels like watches, I wanted to talk about measuring time and how that has progressed the human race. So that every time you look down at that watch on your wrist, you get a sense of a wonder of where its creation has taken humanity. Now, I'm not a physicist, but we are going to talk about some fascinating physics. I just find this stuff seriously interesting. So let's get into it. So the first thing to think about is, why did we measure time in the first place? Now, humans began measuring time for essentially survival needs. As humans living on Earth, we would have noticed the patterns of the day, the night, the phases of the moon and cycles of the seasons just by living on this planet and by being observant creatures. And tracking these events, they helped us to understand when certain plants might bear fruit or when animals might be migrating. And understanding the seasons helped us understand when planting and harvesting those seeds were likely to be most successful. It helped us to really utilize the planet's conditions to our advantage. So in essence, our earliest clocks really were the day and the night, and the cold and the warmth and the wetness of the seasons. And then came coordination of our communities. As human living changed and societies formed, we had requirements to do things at the same time of day to coordinate our efforts. And that requires a shared reference of time. To know when someone might be coming to help in certain activities became very useful. And our earliest kind of clocks were sundials, using the sun to actually cast a shadow across a drawn clock face, essentially, and using things like water clocks to keep time during the night, and of course various calendars. As humans progressed, religion and ritual became more important as well. And timekeeping was very important for religion and rituals. Many ceremonies were aligned with various parts of the lunar cycle. Monasteries rang bells at fixed hours for prayer. And mechanical clocks were spreading through human lives to regulate their daily life. So timekeeping really reinforced social and spiritual order. So then came the age of exploration. This period was a period of European global discovery and colonization, and it overlapped with the Renaissance period, which fostered an interest in knowledge and scientific advancements and economic expansion. So exploration of our minds. In order to navigate the seas safely, though, in those days, John Harrison created the marine chronometer to help determine our longitude in the seas. Latitude was more readily calculatable about our position angle from the sun at noon, or the North Star angle compared with the horizon at night. Longitude needed us to understand that the Earth rotates 360 degrees in a 24-hour period, i.e. about 15 degrees per hour. So to know your longitude, you needed to compare your local time, where the sun position overhead was at its highest, i.e. noon, and compare that to when noon would be at a fixed location, i.e. you set your chronometer to Greenwich Meridian time. The time difference would tell you how far east or west you were, and 1 hour time difference would be 15 degrees of longitude. And you would find your local noon using a special device called a sextant, and that would work out when the sun was highest in the sky. So you knew it was noon at that point, and then you could check your chronometer and see when noon was going to be at that point and work out how far east or west you were. Of course, prior to being able to measure time accurately, uh, a different method was used, and this involved calculating the lunar distance. But this was laborious. It required long-winded calculations. It might be hindered by local environmental factors like cloudy skies, and errors could well mean hundreds of miles off course. And when you're doing this dangerous exploration at the time, it could well mean death. So in order to expand and explore, we needed an accurate timekeeper to determine our position in the seas. And this was all before, of course, GPS navigation, which in itself requires an understanding of how time changes with both speed and gravity. And what about work? Well, time was pivotal in the industrial revolutions, and these were periods when the global economy was improving and increasing efficiencies in manufacturing processes. The precise start dates of this were debatable, but occurred around about the 17th century. But in order for this period to work, things needed to be punctual, shifts needed to be created, transport links needed to run at certain times, financial markets need to run based on certain times as well. And suddenly time was money, and the clocks became a central part of organising our schedule. Now, how do we define time? Well, of course, the first unit of time was simply a day. The light. I can see now, I can't really see now, it's nighttime. But then the ancient Egyptians divided the daylight into 12 parts, so-called hours. And at night they used water clocks and star movements to divide the darkness into a further 12 parts. And we still use 24 hours in one day. And the minutes and the seconds, they came from the Babylonians, as far as I'm aware, who used base 60 number systems, dividing the minutes or the hours into 60 minutes and the minutes into 60 seconds. Now, the solar or astronomical second became defined as 1/86,400th of a solar day. And that's because the Earth rotated in 24 hours. So you do 24 hours times 60 minutes times 60 seconds, and you get 86,400. And this worked pretty well because we didn't need it to be super accurate at the time. But the Earth's rotation is not stable, and that's due to varying geological phenomena. So if you start using the Earth's rotation as a definition for your second, your standard is not reliable. And so therefore we transitioned to using atomic time. And in 1967, we defined 1 second as a set number of oscillations of a cesium-133 atom. Now, this was stable and it was predictable, and it took us away from Earth's imperfect rotation. Now, the day is basically measured against the atomic second. So, of course, this leads us on to, why isn't the Earth's rotation stable? Why doesn't it match up to atomic time? Well, this is thought to be due to one, or the main way is tidal friction. Now we've got our silent but beautiful partner floating in the skies at night, the moon. And the moon, being a massive object, exerts a gravitational pull on the Earth. And its gravitational pull basically pulls the seas into tidal bulges. And this changes the mass of the actual Earth, which affects the rotation. So as the Earth spins and this moon orbits, these bulges transfer energy to the spinning rotation of the Earth. Now, the second way is through the atmosphere and climate effects. Winds and storms and seasonal shifts in air pressure, they can change the Earth's rotation faster or slower. So things like El Nino, that can shift the ocean masses and fractionally change the Earth's rotation. And we're talking microseconds or even fractions of microseconds here. And other geological activities can also change the Earth's rotation. Things like earthquakes and glacial changes. These big earthquakes, they can shift huge masses of the Earth. I think the 2004 Sumatran earthquake shortened the Earth day by a couple of milliseconds. Now, of course, with climate change, the melting glaciers of water, they redistribute around the planet. Now, when you take water from the poles and it's melting into the ocean, that's going to change the Earth's spin. A bit like if you watch figure skating and you see the figure skater with the arms outstretched and the arms in. When the arms are in, i.e. the actual water is locked in at the poles, the figure skater and the arms are in, the figure skater turns faster. When the bulge is more towards the actual centre of the Earth as the water redistributes, it's like the arms are out on the figure skater and their spin slows. Other things that can affect this is the Earth's core dynamics. The movements within the actual liquid outer core of the Earth can also redistribute mass and change the way the Earth actually spins. So in general, the Earth has actually been slowing down for some time in comparison to atomic time. So we've been adding seconds at certain points of the year to cater for this. And now, of course, you're not really going to notice this, but they're there. They have been done. Leap seconds have been added to cater for this mismatch between Earth's rotation and atomic time. However, more recently, the Earth's rotation has started to slightly speed up. And again, this will be due to varying balancing factors of these things and also unknown things that are happening to the Earth to change its rotation. So you can see how understanding time and measuring time has helped us develop in agriculture, in early exploration and navigation, the industrial revolutions and the Renaissance periods in science and engineering, and also now in more modern systems like GPS. That wouldn't work without a knowledge of time. The internet and transportation networks as well, they wouldn't run without a knowledge of time measurement. And so that leads us on to the part that I find really, really interesting and fascinating, how knowledge of time measurement has led us onto these incredible concepts, and it absolutely blows my mind. And that's in the world of physics and its everyday applications. So you understand by now that we would not know the universe in the way that we do, or the movement of the celestial bodies, and your GPS in your car and smartphone would not work if we could not understand time. But how? Well, we know that time changes based on relative speed and gravitational intensity, and that is how we get certain things to work well, like the GPS in your phone. Now, Isaac Newton, you've all heard of Isaac Newton, hopefully heard of Isaac Newton, the guy, apple on his head, gravity, celestial bodies, mathematics, physics, an absolute genius, a behemoth in the world of academia. He treated time as absolute, flowing in this uniform manner. Now, without going into the complexity of the thinking or how time worked in Newtonian's mind, because A, I don't understand it, and B, I'm definitely not smart enough. So, but it was thought that for time to be uniform, the speed of light had to change its speed relative to the movement of the observer. So we'll give a little analogy here. So if you had a person holding a ball on a train, the train was going 50 miles per hour, and this person throws the ball forwards at 10 miles an hour. Now you, as an observer on the platform outside of the train watching through a window, you would see the ball moving at 50 miles an hour of the train plus the 10 mile an hour that it was thrown at, so 60 miles per hour. And that was how they expected light to behave. So if light, for instance, is moving at 300,000 kilometers per second, and you move towards it at, say, 30,000 kilometers per second, you should be able to measure the light moving at 330,000 kilometers per second, the addition of those two velocities, basically. But this was called into question when ultra accurate time measuring devices showed that the speed of light is actually constant no matter what direction it was going in or how we observed it. The speed of light never changed, and so that meant something else had to give. So in comes Einstein, the E equals mc squared guy, the absolute another behemoth of a brain in physics. And he leaned into that concept that the speed of light is constant, because that's what science is, right? Science uses observations of the world as they are, not what we would like it to be, to fit something else. So he brought in that it is time itself that must flow differently depending on the speed you move, and of course the magnitude of the gravitational effect surrounding you. And this became known as Einstein's theory of special and general relativity. Special relating to your speed of movement, relating to an observer, and general relativity relating to gravity. Let's try and explain a little bit why time had to change. It was basically that scientists realized that the maths didn't add up if both time and the speed of light were constant, because observations were, like I said, telling us that light speed was constant no matter what. And my simple brain needs to think of it as that equation that speed or velocity is equal to distance divided by time. So if speed is always constant, either distance or time have to give to compensate to make speed always the same. And in Einstein's theory, it's time and space that give way to allow light speed to remain constant. Now, this is obviously not the full explanation of things. They use all sorts of transformations in their equations, and this is very, very simple way to look at it, but it's reasonable. I think it's a reasonable mental model for someone like myself. You could think about it like that film Flight of the Navigator, where that alien's like, compliance, that one, where the kid goes light speed on an aircraft and he comes back to Earth and he's exactly the same age, but everyone else around has actually aged 20 years. This is Einstein's special relativity at work, because the closer you get to light speed, the less time ticks for you. So, and in actual fact, when you get at light speed, time no longer exists. So for things like photons of light, time hasn't passed at all because it doesn't exist for them. And we can actually even test this time shift happening in real life. And so in these large particle accelerators like at CERN, physicists, they can actually accelerate a particle with a known decay rate, close to the speed of light, and watch how long it takes to decay. And sure enough, when you accelerate these particles faster and faster and faster, they take longer and longer and longer to actually decay, showing that the particle is actually aging more slowly relative to the observer, suggesting that, time is changing. It's absolutely crazy. So anyway, without being able to measure time, we wouldn't have been able to measure the speed of light, and hence all of these wonderful theories of how the universe works, they just wouldn't exist. So how does this all fit into making our navigation systems work that we use every single day? I mean, I use it to go and find all sorts of things daily, like where's my local boots? For your GPS to actually function, you need a satellite to be orbiting the Earth, loads of kilometers above us, and they're moving at vast speeds relative to the Earth themselves. Now, these satellites essentially, they time how long signals take to travel between your device and themselves. Now, if you think back to that equation that I said, that speed equals distance over time, well, you can rearrange that, and distance equals speed times time. So tiny differences in time can result in, hundreds of meters off in distance, which would make navigation very, very difficult if you're hundreds of meters away from something you were trying to find. Now, satellites, like I said, they're moving, around about 14,000 kilometers an hour relative to the Earth's speed. So according to special relativity, the moving clock of the satellite will tick more slowly. And so satellites will lose several microseconds per day relative to Earth clocks due to these speed differences. But that's not the only thing that's happening, you see, because general relativity also applies here, where the gravitational field causes time to change as well. Think about that film Interstellar, where they're near a black hole, this massive gravitational field. And that causes time to tick more slowly for them compared to an observer. So in that particular film where they were near some black hole, I think called Gargantua or something, every few minutes where they were would equate to several years passing on planet Earth. Now, if you think satellites, they're actually further away from the Earth's gravitational field, so the gravity surrounding them is weaker compared to the clocks on Earth. So what does that mean? Well, because the satellites' clocks are in a weaker gravity field, their clocks actually tick faster. So the effect is for them to gain a number of microseconds per day relative to the Earth due to general relativity. So hang on, their amount of time that they're gaining and losing is different between special and general relativity. Well, yes, you have to net off the effects and adjust the clocks for both of those things. If you don't, then the satellites will be something like 40 microseconds faster per day than Earth clocks, which equates to a number of kilometers off, which is utterly useless for GPS. So we actually have to correct for these time differences, and that would give you your accurate GPS. So, in conclusion, without a measure of time, we would be nowhere. We would be living perhaps simpler lives with much less complexity, certainly missing some understanding of the universe around us. We would be perhaps in our primitive states. Whether this is good or bad, it will depend on how you view human evolution at the moment. Are we a blessing, or are we a disease of the planet? Or are we both? Because they don't have to be mutually exclusive. In addition, our advancements brought about perhaps an unnatural state for humans to live in, with far more stress, segregating our time so efficiently, maybe leaving many of us stressed out and, ironically, with little spare time to look after ourselves in a way that can prevent the onset of chronic disease. Like everything in life, there are good and not so good consequences of our actions. But when we look down at the little device on your wrist, we can look at human evolution through the ages and our progression from where we were to where we are now. And if you have a quartz watch measuring time on your wrist, its quartz vibrational workings required an understanding of how to measure time itself to make it. So it's a time measuring device that requires an understanding of time to make it. Is that a paradox? Probably not, but anyway, this talk was just a little musing on measuring time. I hope it helped you look at the world with a little bit more wonder today. And anyway, it was a fun experiment for me to learn some new skills and play about on YouTube. So hopefully it was interesting. I hope you keep that sense of wonder. So take care of yourselves and those around you.